Hello children, welcome back to the channel. Apologies, I could not upload any videos last night due to certain health issues. Anyways, I'm back now. So we'll be continuing our discussion from the previous video, and today we'll be taking up the case of perfectly inelastic collision in one dimension first. So in this case, what happens is that to be perfectly inelastic in a collision, what needs to happen is that the two colliding bodies or the multiple colliding bodies after a collision must gel together, coalesce and form a single body and move as a single body. For example, I have already explained that one of the problems that I had given in my previous video, one of the previous videos, where a bullet was moving and it hit a stationary wooden log, and so it got embedded to it, and the wooden log and the bullet together started moving. So that was a case of an inelastic collision, perfectly inelastic collision. So let us say, for simplicity, we have a mass of m1 moving along positive x direction with a velocity of u1, and it hits another mass of m2 which was initially stationary, that is to say u2 equals to 0. So after the collision has taken place, the two masses coalesce together and then they will start moving with a velocity v. This is m1 and this is m2. So this is a case of perfectly inelastic collision. Two bodies collide and then they form a single body, and the body moves as a single body afterwards. So in this case also, as we know, in this case also, we know that conservation of momentum, linear momentum must hold good. So if we consider the momentum before the collision, it is m1 into u1 plus m2 into u2 is 0. So the net momentum before collision is m1 into u1. What is the net momentum after the collision? After the collision, of course, the two bodies coalesce and so they form a single mass of m1 plus m2, and the whole mass moves with a velocity v, which will give us the velocity with which the two masses move together is equal to m1 by m1 plus m2 whole thing multiplied by u1. Okay. Now, if it is so, then what is the initial kinetic energy? Let's say K initial. Before the collision, what was the kinetic energy? Clearly it is half m1 u1 squared. And what is the kinetic energy after the collision? This is half m1 plus m2, the net mass, into v squared. Right. So now let's consider this. We had mentioned that in case of inelastic collisions, total energy is conserved, however, total mechanical energy is not conserved. In other words, mechanical energy gets converted to other forms of energy like heat, sound, etc. Right? So if it's an inelastic collision, the kinetic energy, being a part of mechanical energy, is not conserved, or whether it is conserved or not. If it is conserved, then initial kinetic energy must be equal to final kinetic energy, right? So let us see what is the difference between these two kinetic energy. That is to say, delta K, which is equal to K initial minus K final. Okay. Now to find this, first let's get back to here and find out that half this final kinetic energy is equal to half m1 plus m2. Now v is given by this expression, right? V is equal to m1 by m2 into m1 by m1 plus m2 into u1. So we substitute this value, we get m1 square by m1 plus m2 whole square into u1 square. So what we can do, what we can do is that we can, sorry, not this, remove the power, and so we will be left with half m1 square u1 square, whole thing divided by m1 plus m2. Okay, so if you substitute this value in this equation and value of Ki in this equation, we will be able to find the difference between the kinetic energies. So if we substitute these values, this becomes equal to K initial is half m1 u1 square minus this one, right, half m1 square u1 square by m1 plus m2. If we take half m1 u1 square common, is equal to half m1 u1 square. So we will be left with 1 in the first term. Second term, what we will be left with? We will be left with minus m1 by m1 plus m2. If we simplify this, what do we get? We should get half m1 m2 m1 m2 divided by m1 plus m2, whole thing multiplied by u1 square. So this is the difference of initial and final kinetic energy, which is of course greater than 0. Why? Half is greater than 0, mass cannot be negative, and u1 square, a square term, real term, must be positive, which means initial kinetic energy, that is to say initial kinetic energy is greater than final kinetic energy. In other words, sum of the kinetic energy of the oncoming particle is lost during the process of the two masses coalescing in the form of heat or sound or any other form of energy. So the net kinetic energy at the end of the collision is less than the kinetic energy at the beginning of the before the collision. Now if we take the ratio of these two, that is to say Ki by Kf, or sorry, Kf final to initial, the fraction of kinetic energy. Okay, so what will be this value? This will be again the same, half this one, right, m1 plus m2 into v square divided by half m1 u1 square. If we substitute the value of v square from here, we get this is equal to half we cancel, right, so we don't need to put half. This is m1 plus m2. Instead of v square, we will write m1 by m1 plus m2 whole square into u1 square by m1, right, into u1 square. u1 square will cancel out. This is whole square term, this one v square. So we are left with m1 by m1 plus m2. Now clearly this term must be less than unity. Why? Because m1, the first mass, must be less compared with the sum of the two masses. Okay, that is to say Kf is less than Ki, because this is Kf by Ki. Now if it is so, and if we consider a special case where m2 is much greater than m1, that is to say if m1 is negligible compared with m2 In that case, in this fraction, the numerator term is negligible, or we can set it to 0. Or in other words, what we will have, kf by ki will be equal to 0, giving us kf equals to 0. So if a small or body of small mass hits a very massive object and gets embedded to it, then body that is formed after this will not have gathered any speed or any kinetic energy. Kinetic energy is 0, means the speed with which it moves becomes 0. So if a light object, very light object, hits a very massive object and gets embedded to it and has a perfectly inelastic collision with it, then the massive body or the system will not gather any velocity or will not gather any kinetic energy. You can see it as an example, like if you hit a heavy sandbag with a bullet, the bullet gets embedded to it, but the sandbag does not move. What happens there is that whatever kinetic energy the bullet was carrying gets converted into other forms of energy, be it heat, be it sound, or any other form of energy, and it doesn't impart any kinetic energy to the next body. Alright, now let's take up the case elastic collision in 2 dimensions. Now here what happens is that, let's say a body of mass m comes along the positive x-axis, it moves towards the positive direction of x-axis, and another mass of m2 is stationary. For simplicity, we'll take it as a stationary object. Let's say it's at the origin. So when the first mass comes and hits the second mass, the two masses now do not move along the positive axis, rather they move in 2 different directions. That is to say, let's say the first mass moves like this, and let's say the second mass moves at some other angle. Let's say it moves like this. Okay, so let's say the second mass reaches here and it has a velocity of v2, and the first mass which reaches here has a velocity of v1. So the mass number 1, m1, makes an angle theta 1 with the x-axis, and this mass number 2, m2, makes an angle of theta 2 with the x-axis. So this is the case of a 2-dimensional collision, because we cannot set it anyway so that it falls along one of the axes. We have to take the entire plane for this particular case. So what we will do is that in such cases, what we normally do is that we resolve the velocity vectors or resolve the vectors so that we can find the required equation along and perpendicular to 2 directions. What we will do here is that we will resolve this and this vector, these velocity vectors, along x-axis and perpendicular to x-axis, that is along x and y-axis. So what will happen for this v1, this velocity will be resolved like this. This will be theta 1, so it will be v1, cos theta 1, and along the y-axis it will be v1 cos theta 1, and similarly v2 also along x-axis, since this is theta 2, this will be v2 cos theta 2, and this will be v2 sin theta 2. So what we will do, we will apply our conservation laws. What are the things that are conserved in elastic collision? We know that momentum must be conserved, and also we know that kinetic energy must be conserved. So what are the conservation rules? First, let's consider along x-axis. Momentum must be conserved. So what is the initial momentum along x-axis? The mass was moving towards the positive x-axis, so initial momentum is m1 u1. What is the final momentum? Momentum x component of momentum of m1 and x component of momentum of m2. So this is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2 along y-axis. Since the second body was stationary, first body was not at all moving, so along y-axis initial momentum was 0. However, final momentum v1 cos theta is along positive x-axis, so it is v1 sin theta. Oh, this is not cos, this is sin theta. v1 sin theta 1. This one is along negative x-axis, y-axis. So this will be minus m2 v2 sin theta 2. Also, we know that kinetic energy must be conserved. So if we consider the kinetic energy, we must have half m1 u1 square must be equal to half m1 v1 square plus half m2 v2 square. Since kinetic energy is a scalar quantity, we just need the magnitudes of the velocity. We do not need to resolve the components. So we have three equations: number 1, number 2, and equation number 3. Right. Now we have three equations, and we have how many unknown variables? See, we have theta 1 that we need to find. We have theta 2 that we need to find. We have v1 and v2. That is, if we know the condition before the collision, and to find the condition after the collision, we need these four variables to be found: v1, v2, theta 1, theta 2. So we have four unknown variables, whereas we have three equations. So we know that we cannot solve it absolutely. For four variables, we need at least four simultaneous equations, right? So if one of the values are given, we will be able to solve the problem, or one of the values are experimentally found, we can solve this case. Otherwise, it will be difficult for us to solve, or will not be possible for us to solve it. However, we can always consider certain special cases. So the first special case is that of a glancing collision. Now when we call a collision to be glancing, is that when theta 1 equals to 0 and theta 2 equal to 90 degree. So the mass m1 comes and just glances the second mass, and so m1 will continue in its path without getting any deflection. And since m1 doesn't get any deflection in the direction from its direction, m2 will tend to move perpendicular to the direction. Okay. Now in that case, if we consider these three equations, equation number 1 will give us that what? m1 u1 must be equal to m1 v1 cos theta 1 is 0, so 1. m2 v2 cos theta 2 is 90 degrees, so second term will be 0, which will give us that u1 equals to v1. That is to say, the oncoming mass m1 will move along the positive x direction only without any change in the magnitude of its velocity or any direction change in its velocity. So it will continue with its initial velocity. If we consider equation number 2, here 0 equals to sin theta 1 is 0, so first term will be 0 minus m2 v2 sin theta 2 sin 90 degree 1, which will give us v2 equals to 0. So the second particle will not move at all. So v2 will be 0, so the third term will be the same with v2 0, right? So m1 u1 square must be equal to m2 v2 square, since m1 equal to v1. So this is one of the special cases which is known as the glancing collision. Now, the second special case is known as the head-on collision in 2D. What do we mean by head-on collision? Well, if you look at this way, see, in this case, if there is a head-on collision, theta 2 must be equal to 0 degree. That is to say, M1 comes and hits M2. M2 gets scattered at some angle theta 1. M1 gets scattered at some angle theta 1. No problem. But M2 will move along the positive x-axis. If so happens, then what we get from these equations? We must have, from equation number 1, M1 U1 must be equal to M1 V1 cos theta 1 plus M2 V2 cos theta 2 0, so it's 0. Second equation will be 0 equals to equation number 2, M1 V1 sin theta 1 right. And finally, third equation, it will not get altered at all, it will remain the same. Equation number 3 remains. Now if you look at this, we have three equations, this one, and this one, and we have three unknown variables, V1, theta 1 and V2. So we will be able to solve this equation. Alright, now let's take up the third case of when M1 equals to M2 equals to M. That is to say, the two particles have the same mass. In that case, the equation for kinetic energy, half this one, equation 3 will give us M1, M1, M1. All the three masses are equal, so we can divide both sides by M, and then we get halves are taken away. So we have U1 squared equal to V1 squared plus V2 squared. This is one equation. Also, if we consider conservation of momentum, now we had resolved these components to find two different equations. If we consider in vector terms, then we must have M1, that is M, U1, vector U1 must be equal to M1 V1 plus M2 V2. But since M1 and M2 are equal, we can rewrite this equation as U1 equal to V1 plus V2. Fine. If we take dot product of it with itself, we get U1 dot U1 must be equal to V1 plus V2 dot V1 plus V2, which gives us U1 squared. Left hand side, dot product of vector with itself is just square of its magnitude, right? Right hand side will be V1 dot V1, V1 squared, V1 dot V2 plus V1 dot V2 plus V2 dot V1, and then V2 dot V2, that is V2 squared. Now since dot product is commutative, so we can rewrite this equation simply as V1 squared plus V2 squared plus 2V1 dot V2. Okay, now if I say this equation is equation number A and this is equation number B, then equations A and B, what do we get from these two? A and B will give us, left hand sides are equal, right? V1 squared. So V1 squared plus V1 squared must be equal to V1 squared plus V2 squared plus 2V1 dot V2. Right? Or we can say that using equation A and B, we can simply say that 2v1 dot v2 equals to 0. Or we can remove the factor 2 also divided by 2 and we get v1 dot v2 is 0. But we know v1 and v2 are non-zero vectors. So what should be the condition under which this is possible? There is only one condition under which that is possible, which is v1 is perpendicular to v2. So what it means is that if there is a two-dimensional collision between two equal masses, then after collision the two masses will move away, making an angle of this angle between the two vectors, two velocity vectors, v1 vector and v2 vector. This angle must be equal to 90 degree. They must scatter at an angle of 90 degree.